We are in Chapter 7's exam review. We're going to be using algebra to describe patterns of change, looking at exponential growth, exponential decay, and things of that matter. So starting with 7.1, looking at compound interest, we have a specific formula that we use. So suppose you deposit $1,000 into a savings account. That's your principal, and upon which the bank pays an annual yield of 4.5%. Remember that these turn to decimals. We move it 2 to the left, so 0.45 is 0.04, that's 4%, and then you add the 5 at the end. So that's going to be a decimal version of it. So we're going to write an equation to represent this situation. And so it's always going to be your principal times 1 plus your rate, because 1 represents 100% and you're increasing it by the rate. So 100 plus, which in this case, 4.5%, and it's always raised to the time. So if we're going to write an equation specifically for this, the principal is 1,000. And in here, you can do the 1 plus 0.045 if you want to do that, but you can actually just combine it to 1.045 raised to the t, which we don't have. So depending on the number of years, we plug that in for t. So for part B, how much money will be in the account after 5 years? All we have to do is plug in 5 for t. And so if we run this, we can run all of it right here. 1,000 times 1.045 raised to the 5th. And we're at 12. Oops, I did not put the right equation in there. So it is 1,000 times 1.045. I missed the 4. Raised to the 5th. 1, 2, 4, 6. We're talking money here, so we'll go to 18 cents. So that's how much money is in the account. Now, how much interest did you earn? Interest is how much you've actually made on top of what you invested. We invested 1,000, and now we have 1,246. Well, 1,000 of this is the original 1,000 we put in. It's not new money that we made. So we need to take the 1,246.80, or 18, not 80, and subtract the 1,000 that we started with. And that comes out to $246.18. So that's the interest that we made, and this is the total amount of money that is now in the account. And so this formula holds true for all of our exponential problems. It's either 1 plus if it's exponential growth, or 1 minus if it's exponential decay. It's going to be less than 100% because you start with 100% and it goes down. So starting with exponential growth, the price of making a t-shirt starts at $7 and increases by 20%. So write an equation to represent the situation. So the equation here with our variables is y equals b times g to the x. B is what you begin with, g is your growth factor, and it's raised to your time. So in this case, y equals what you started with, which is 7, times. Now, your growth factor is either 1 plus or 1 minus. Since this is an increase, it's 1 plus 20%. 20% is 0.20. Move it 2 spots to the left. And so when I multiply, if you like to keep it consistent, you can put the parentheses so it looks just like your compound interest. It'd be 1 plus 0.2, which is 1.2. And then that's raised to the number of years. And then we're just going to go ahead and use that here. So what's going to be the price in 6 years? So 7 times 1.2 raised to the 6, not 7. So 7 times 1.2 raised to the 6th power, $20.90. Okay, now exponential decay is the same thing, except it's not going to get larger. It's going to get smaller. So it's 100% minus however much. So a new piece of industrial equipment costs this much. It depreciates or goes down at a rate of 12%. 12% is 0.12. Write an equation to represent this situation. So y equals our beginning amount, 2,470,000, times our growth factor. So if I write this out, it is actually 1 minus 0.12. It's 100% minus 12%. We're going down 12%. So we want to simplify that. So we've still got this out front. And so if we take 12% off of 100%, you're left with 88%. So if it's decreasing 12% every year, that means you are left with 88% the next year. And so now we're going to go ahead and solve this for the given number. So 10 years. So every year it goes down 12% for 10 years. And we are left with $687,897.41. All right, looking at these graphs and specifically looking further at these growth factors. So considering the general equation, which we just talked about a bunch, what would the value of G be, which is your growth factor? So if we are decreasing exponentially by 6%, which is 0.06, not 0.6, that'd be 60%. Since it's decreasing, it's 1 minus 0.06, or 100 minus 6%, which is going to be 94%, which is 0.94. Increasing is 1 plus the percent, which is 0.192. You move it 2 to the left. You move it 2 to the left. Okay, so it's 1 plus 0.192. And so my growth factor, when you put it together, is 1.192. And no change. So think about, you're starting with something, and when you multiply it by the growth factor, nothing changes. So what's the number if you're multiplying and nothing changes? That is 1, not 0. It would change if it was 0. It's 1. Okay, which of the following graphs would exponential equations be good models? So if I look at this first graph, the data is not perfect, but that looks to be linear. Okay, so that is not exponential. This looks like it's curving up and is exponential growth. Okay, so that's good. This seems to be curving down, and that's exponential decay. So that's good. And you could argue that this maybe is linear. You could also say that there's no pattern, because it's not really clustered close enough together to say linear. It's kind of all over the place here. And so this is no good in terms of modeling exponential something. Okay, moving on to 7.5. We're going to look at continuous and discrete. So continuous is when everything is connected, and discrete is when things have holes in it and there's spaces. So stating the domain and the range after that, that is all the possible x values for domain, all the possible y values for the range. So first of all, starting here, continuous or discrete. This is all broken up. We're not including everything in between these whole numbers. And so we would call that discrete for our domain. We have to list all of our x values. And so we have an x value of 1 and 2 and 3 and 4 and nothing in between. So we can't say everything greater than or equal to 1 and then less than or equal to 10. It is actually just the list of 1, 2, 3, 4, 5, all the way up to 10. So 7, 8, 9, 10. Range, our range, again, is all of these possible numbers here. We don't have the exact numbers, so we would have to guess a little bit, but this looks like 1 and 4 and 9 and 16, 25, and you would continue listing that. You can see the answers on the answer key, but it's each and every one. We can't write this as an inequality because not everything is connected. When we get over here, this is continuous. First of all, it's continuous because it's completely connected. And when we go to do our domain and range, these we're going to write as an inequality because it includes everything between. So let's just looking at the domain, the x values. It goes from here to here. Every value between these two numbers is part of this solution. Okay, it's connected. It doesn't jump from one to the next. It's not broken up. It is continuous. So everything from negative 10 to positive 10 is in it. And so we have to put the x in the middle, and we say x is greater than or equal to negative 10 and less than or equal to positive 10. And for the range, our lowest range here is 0, and our highest is 100. And so we're going from 0 to 100. So 0 and 100. And we're talking about the y values. So y is greater than or equal to 0 and less than or equal to 100. 7.6 now, function notation. So here's our function. We're going to evaluate based on what's given to us here. So we have f of 2, we're going to plug 2 in for x. F of negative 10, we're going to plug negative 10 in. And then here we have two separate problems to solve, and then we're going to add them together at the end. So f of 2 means plug 2 in for x. That's all it means. And so we're going to have 10 minus 19. I lost my key. There we go. 10 minus 19, and so we're going to have negative 9. When I have f of negative 10, I'm plugging in negative 10. So 5 times negative 10 minus 19, so that's negative 50 minus 19. That's negative 69. And then over here, we have to solve this separately. So we're going to do, first of all, find f of negative 5. So 5 times negative 5 minus 19. Plus, so this is like an entire quantity, f of 4, which is 5 times 4 minus 19. So we have to solve both of them, and then last thing we're going to do is add them together. So we have 5 times negative 5, and that's negative 25 minus 19. So that's negative 44, and that's going to be added to this solution. 5 times 4 is 20, minus 19 is 1. So negative 44 plus 1 is negative 43. And last but not least, we have to be able to recognize linear and exponential graphs. So first of all, I know this is linear, y equals mx plus b. I know this is exponential because we have the exponent. This is exponential, and this is linear because it's y equals mx plus b. So dealing with the linears, we've got this one and this one. One's going up, one's going down. That's all based on your slope. Slope is negative 2, slope is positive 0.5. So the one that goes up is this one right here, if you just want to draw a line. It hits at negative 2, that's the intercept, and then goes up by 0.5. This one would be right here. It hits at 7 and then goes down at a slope of 2, negative 2. Now for these exponential ones, you have to look at the growth factor. If it's less than 1, that means it was 1 minus a percent, and that means it's decay. And so that's like this, where it curves down. And if it's more than 1, that means it was 1 plus a percent. And so that's going to curve up and